Okay. Waited enough time that anyone that's lost should be able to find. Today's going to be kind of a light lecture because I'm going to start ramping up for the next lab. So there's going to be an exam on Thursday. However, there's been a minor outbreak of COVID amongst students in my courses. And so I'm not even going to try and do it in person. So there's a couple different ways that I will do the exam. I just have to figure out which one works best. The most likely is just at 5 o'clock, I will post a file. You take it, you have an hour and a half to go ahead and upload it, right? I don't want to do a full take-home exam because to make that even remotely workable, it has to be way more difficult than necessary. And so I'll just still do timed so I can keep it mostly conceptual. You're not going to be doing a giant metric ton of math. It's mostly going to be algebra and concepts, right? And it's not even going to be as hard as anything that was that homework one or the lab one. So it's conceptual because in my estimation, after doing this class so far, the next time I teach this, I'm not even going to have exams. I just think it serves better as hands-on, and then doing like quizzes, essentially, which is what this will be to make sure that you get the concepts of what I'm trying to teach. So I'm going to go through kind of the concepts that I want to make sure that you know this time. So I'll start out with a review, and then I'm going to talk about filters, which I know if you've taken 3120, you've talked about filters, but 3120 is not a prereq for this course, only 3110 is. So make sure that everyone knows what filters are, which I assume you do because you took signals, but that may have been a long time ago. So I'm going to assume that you guys don't know anything, right? I'll assume that you know like inverting and non-inverting amplifiers, and that's it. Now, with filters, when I get to that, I'm not going to make you like do all the algebra that they did in signals, right? I'm going to make you guys design filters like engineers design filters, which is we're going to find a filter calculator and we're going to plug the numbers in, right? That's how you're actually going to do it. That's how we're going to do it. And I'll use that to launch into lab 3, I guess it would be technically, right? Because the first one was just bridges. The second one was the bridge plus instrumentation plus the sensor. And then lab 3 is looking to be one of two. I think it's going to be an audio lab. We'll talk about, so next week we'll have lectures that involve like talking about audio sensors and signal generation and that kind of thing. And then we'll start the lab, which if I can test it in time, I'm going to try and have you guys build some active noise cancellation circuits is what we'll try and build. That's my target because I think it's fun and educational and talks, and it's one of the examples that I like to bring back, right, where that I talked about way back in the beginning when we were actually still in class, where I mentioned that sometimes you take a signal and you feed it back around and you apply that stimulus to the circuit in order to keep like a balanced bridge or a balanced input or whatever. That's all active audio cancellation is, right? To do that though, unsurprisingly, audio filtering requires signal conditioning, which requires filters. So hence, we'll talk about filters today so that you're not completely lost in the case that you've forgotten everything from signals and never took 3120. It's going to be high level, so just be aware. I'm not going to dig into the nitty gritty, and I'm going to talk about kind of some of the fun filters. But let's start off with the topic review that's next week. It's pretty short, honestly. The main thing is that, well, I'll just start from the top of this so I don't get confused. So I'm going to start off, probably going to be some question about linear estimation, or at least estimation in general, right? And it could be anything from like, here's samples that follow along this kind of curve. And if I use a linear estimator, right, what is my error? If I give you like those data points, right? What is my maximum error? That kind of thing. I could ask you conceptually, what is the point of using this, like the least squares estimator? What is it good at, right? Is it conceptual? Where does it struggle? I might ask you in this case, like, well, it's kind of parabolic, so I use a linear estimator. Is there a better way to do this, right? That kind of conceptual questions. I could also give you a couple of numbers and say draw out or do the linear estimation using Excel, Python, whatever you want. Basic questions on top of that, I could ask you just, if you remember homework 1, I asked you some questions on like dB questions, units questions, sensitivity, dynamic range, and resolution. Those are the 3. I will stick to those, I think. So dB, units, sensitivity, dynamic range, resolution. Those are kind of the fair game vocabulary words, right? Because those are the ones that we were brought up in these labs, right? So all of these questions are going to be relevant to the labs and the homework that we've done. Obviously, I'm going to ask you questions about Wheatstone bridges, everything from why we use them, why we use different kinds of them, right? What are the different configurations of them do, right? The half bridge, quarter bridge, full bridge. What are the trade-offs of each of these, right? Could ask you more kind of sensors in them kind of questions, which might be like, sorry, I have to come up with a different example. So the one about use is exactly what I'm going to ask on the exam. Let's go. I need some variation in these scores, guys. Theoretically, I don't know if I'm going to get it. But like, yeah, I could do that. So like your sensors, you know, we were using these 4 sensors and we did the half bridge in order to cancel out the thermal temperature. I could ask like, why don't we get a perfect thermal noise rejection? Right? Or how could you do better than what you did in your thermal noise rejection when you designed this circuit? Right? That kind of question. When I say an hour, I'm not sure I'm going to give it even a full hour to take this exam, because if it's that high level, because that's what I want to make sure, right? I want to make sure we understand the topic. So if it is that high of a level and there's not that much time spent writing numbers, I'm just going to give a shorter time period so that I can justify how easy it is to make sure that you kind of understand. I could and likely will ask some questions that you have to do some algebra for the equation that we use, right? Right? I could give you, right? This is the one that you use for strain, right? That's the thing for strain. I could ask you stupid questions like, what is the unit for strain? That's going to be a quick Google question. And then I could also give you a different equation for a different type of force sensor and do things like give you a bridge configuration, right? I could say, this is a sensor, this is a sensor. Given this equation for resistance and temperature, right? Prove that this configuration rejects thermal noise, right? Or rejects the, well, thermal noise is fine for saying it. Technically, I would say rejects the contribution of temperature, right? And then I may, in fact, not even give it to you and say that I could do further and say, you need to design, here's your sensor, it has this equation. You need to design a circuit that will reject temperature, extra pressure, lateral strain, whatever it is. And then you need to figure out, is it additive or multiplicative? Then which side does it go on? I'll give you the equation, you'll solve and show that it resolves it, right? That's like the most mathy question probably that I'm going to give you is going to be in relation to that bridge. The other mathy question that I could give you is considering the amplifiers, right? Given an instrumentation versus a differential amplifier, what is the worst case error? And I would define which error I mean, right? Because this is an error. But I could say like least balanced or whatever, given 5% resistors or 1% resistors or something. Or I might give you exact resistor values and say just calculate what this offset does to CMRR, right? So it's going to be resistors in relation to like how the balanced bridge is affected and how the common mode rejection ratio is affected. And I could also ask the question of like, how is the thermal rejection affected by mismatch? Like mismatch between your sensors, right? Because I could do something like, well, one of them is alpha and one of them is alpha plus 2 or something, right? If they're a little bit different. And I could ask either the algebra for it or just conceptually. Conceptual questions around amplifiers, why you use instrumentation versus why you might use differential, places that it is acceptably used differential. I could, if I really wanted to, give you a sensor, give you an amplifier, and then like a data sheet to reference, give you a sensor, give you a data sheet, and ask you a question of like, is this a good amplifier for this sensor? Right? And then you need to consider things like input current and noise and common mode rejection and things like that. Just looking at the basic terminology, it wouldn't be anything that we haven't talked about as far as specs goes. And it would just be turning the knowledge of sensitivity or CMRR or something into reading a data sheet, right? Just translational knowledge test. Now, lab 2 especially, both the labs apply to this, but the lab 2 especially, because right, this has been a big multi-week project. It's hopefully been educational, and there are questions throughout that. The most obvious thing that I could do is ask you one of those questions, right? I could literally just pull something right out of the lab 2 that hopefully you've done, which isn't due till Sunday, I believe, but if you understand those questions, I could pull right from them. I could also ask questions that are kind of adjacent to them, right? Which kind of goes back to the sensitivity and the op-amp configurations and that kind of thing. But there will be questions that relate to that lab 2, including why did we measure it the way we did? Why did I have you set these measurements up the way I did, right? And I could ask you, well, if I had done it this way, what would that be different? Right? And it should be that you understand that if you understand the result, right? The corollary to that is, what are the sources of error in that measurement? Why are they wrong, right? Because none of your things were exactly right. None of them were perfectly linear, even though it should be, right? Things like that. So sources of error could be a big one. Comparisons, again, of the bridge would fold into this, or an amplifier or instrumentation, and things, and ask questions of ideal versus real. Right. I could ask questions around there of like input full scale, output full scale, tell you like, what is the output full scale of the bridge? What is the maximum input full scale of the amplifier? That's actually my full list of things that I was thinking about asking questions on. I haven't written it yet. There's a slim chance, there's a deadline I'm trying to meet tomorrow for a new degree that we're going to be offering. There's a slim chance that this gets bumped and you just can take it all weekend, whatever. I don't want to do it that way. If I do it that way, basically what I think will happen is I've never done it in Canvas, but I'll set a thing where you just start and you'll have an hour or however long I determine to do it whenever. Don't cheat off of each other. I'm not going to do very much to enforce it. Just don't cheat, right? It is cheating. It would make you fail the class. It's boring. And it does actually help me for you guys to take the test without cheating, because it tells me what you guys do and don't know. Because ultimately my goal with this class isn't to fail you out of it. It is to make sure that you guys are learning useful material for when you go out and get a job, right? So yeah, I will let you know with an announcement how that test will go. Plan on it being just 5 o'clock. Take it from anywhere on Thursday. If you need, for some reason, to not take it at 5 o'clock, you need a different time, you catch COVID and you're in the hospital, etc., send me an email. I'll send it to you separately. I'm not going to be too hard on you guys on that. I understand it's kind of a weird time and COVID is kind of spreading around, because I already have a couple of students that are out with COVID. Yes, I'm going to try and make this not painful, mostly to evaluate what you guys know so that I can use it as feedback and then say that, yeah, I gave these guys a test, right? That's the goal. let's talk filters. And when I say filter, I don't mean it like Dr. Gibbons does to you. I mean, in the high level, I need to use a filter right now, and I'm going to pull out my practical electronics for inventors, right? Which is clearly not very EE heavy, right? This is kind of a hobbyist perspective, but it turns out this is actually really useful. The hobbyist perspective is for designing sensors and instrumentation, because sensors and instrumentation is really where electronics kind of meet mechanics, right? Because sensors are mechanical engineers' domain, mostly opticals are kind of ours, but instrumentation is ours. So mechanicals have to learn instrumentation. We should learn sensors. It turns out sensors are easier, right? Because you just go read one of those terrible data sheets that the mechanical engineers like to write and go like, okay, so it has like resistance or something. Okay, I'll figure out how to use this. There are, right, a couple different kinds of filters you're most going to look at. We're just going to look at basically magnitude versus log scaled frequency is usually how we're going to describe what a filter does, right? The one that you all know how to build is a low pass filter, right? We all know this one. We all know this kind of generic shape. If it's a single pole, it falls off at what rate? There you go. Right. 3 dB is this point, right? And so I'm going to draw this with a little offset just so I don't have to put the red right over. It doesn't really look like this, right? It's not really a corner. What it really means is this point is 3 dB below the pass band, right? So it looks really something like the red, right? It is a difference between this and that. And this is a very important difference, right? This is why when I was talking about in the lab that when you're doing the CMRR test to offset it by a decade, because you've already lost, if you're looking at voltage, right, with 1 by the root of 2, that's what 3 dB corresponds to. You've lost a fair amount of your signal power already. And if you think that you've designed this here and you don't account for that roll off and you reconstruct your signal, right? So there's the idea of de-embedding. This is something that we do a lot of times in like precision amplifiers, where we have this filter cutoff for various reasons that we're limited, but we actually are interested in like frequencies up to here, right? So we can do this thing called de-embedding, where we basically divide by the inverse of this, and so it pushes it up to be flat. And we can actually reconstruct the signal artificially. There is some point where the noise overtakes it and you can't pull any of the data out. But you can extend your bandwidth by like a decade pretty comfortably. But if you're not careful, right, this 3 dB, and I'm like reconstructing a signal and it's smaller than I think it should be, and like, okay, well, this is my impedance. So this is one of the labs that we'll do in the future. We're going to measure the impedance of a complex circuit, right? And if I give it a sine wave and I want to measure the impedance of something across the frequency, and I have a filter with a cutoff frequency, I'm just going to call it F1 for now, right? A cutoff frequency of F1, oh, F1 should be over there, sorry. Cutoff of F1, then I give a sine wave in, and I look at the sine in versus sine out, right? That would, the amplitude change could tell you the impedance of a circuit or something, right? In the simplest way. So this is actually, this box is actually how we model electrodes, like neural electrodes is how we do it. And so in a stupid way, I could apply a sine wave into here, right? And then I could look at the voltage divider and I could actually figure out what the impedance of this is. But if I had a filter on the output to get rid of noise, and that filter had a cutoff frequency of F1, and I looked at the division between the input signal and the output signal, but I wasn't accounting for the 1 divided by √2, now I've reconstructed the impedance wrong because I'm getting roll off. But if I know that this is my roll off, then I can actually just multiply it by a number, well, really an equation, right? And de-embed that error. This is very useful for precision measurements when you're trying to push the limits of anything. Next up, high pass filters, right? They're just the opposite. Low pass filter. For these, actually, I'll come back around to that for a moment. If you combine the two, right, you could build something that looks like a bandpass filter, right? Where I'm only interested in the middle section. I can do the inverse of that, where I am not interested in some section of it. All of these have various uses in them. They're very helpful. Like anything high pass filter, right? I kind of talked about high pass filtering in the integration loop of an instrumentation amplifier, where an integrator is really just a high pass filter and it can remove DC offsets, right? If you're trying to measure a 1 millivolt peak to peak signal, but your amplifier but your sensor might have a DC offset component to it that might be plus or minus 1 volt or anywhere in between, and you just don't know, well, it's useful to throw away that DC signal, so you make a high pass filter. Once again, you're losing some ability to measure lower frequencies, right? But it can be beneficial. Easy example for this one, like, is radio, right? The bandpass, where all you're doing is you're tuning where your bandpass filter is when you turn that knob, or more like push buttons these days, right? They got to change the analogies for modern times, right? You scroll through, and what is X96 still popular? No one listens to the radio anymore, do they? I don't either. But right, if you want to tell it, the 96.3 really is just a description of what frequency it's at, and it just moves this bandpass filter around so that you hear that one radio station and not all of them jumping over all each other, right? Same thing works in essentially cell phones. Of course, cell phones are way more complicated than that because we need to be able to have thousands of cell phones within like a football arena, for example, right? So hopefully Dr. Hearn, or is he already teaching? I don't know. We're supposed to have a digital communication class that will talk about some of that stuff. That should be pretty fun. Right now, yeah. So he should be covering some of that in that class. If you're not taking it now, you should take it in the future if you're still around. Notch filters are really helpful. The most common thing you'll use the notch filter for is to get rid of 60 hertz noise, especially in low frequency sensor measurements, because 60 hertz noise comes from the power lines, right? And it's not just 60 hertz, but because the third harmonic turns out so 180 hertz of the 60 hertz, it's sometimes bigger than the 60 hertz noise itself. But filtering out the 60 hertz noise at the beginning can reduce the harmonics, right? Makes sense. If this initial signal is smaller, its harmonics should be smaller. So this, very helpful for filtering out 60 hertz noise. We use this, so my perspective is mostly biological data, right? I do biosensors. We'll do a lab in biosensors, I'm pretty sure. Not next, but the lab after that. And 60 hertz noise poses the same problem because it turns out our bodies work really well as antennas. There's this problem, if I'm measuring precision signals, right, I want to put a Faraday cage around it and block out signals. Well, 60 hertz noise is such a low frequency, it doesn't really care very much about the presence of a Faraday cage. There's materials that you can use that are designed for low frequency interference, but your typical kind of like copper mesh Faraday cage is a really typical one. It doesn't deal as well with low frequency noise. So high frequency, let me make sure I get this right. High frequency EMI tends to be carried along the surface of your shield, okay? So if I have, I'm not the world's greatest artist, and I apologize. I'm just going to go to copper mesh, right? Interlinked copper mesh. And high frequency signals hit this, they're going to follow along the surface of that. Low frequency EMI tends to be transmitted in the bulk. So in this case, it would be the center of these wires. But these wires are typically not very thick because it turns out copper is really expensive, right? And so in order to build a low frequency Faraday cage, you need, well, there's one metal called new metal, I believe is what it's called, which its whole point is to block low frequency EMI. But it's very, very expensive. So instead of spending all the money on this or new metal, you go and notch out the filter. Now, in biological signals, that kind of sucks because you're just accepting that I'm going to throw away any data in this region. But it was bad anyways. I may as well prevent it from ruining the rest of my signal, right? So that's why we use notch filters. You also see them, especially on like audio amplifiers have them, right? Because 60 hertz is within most people's normal hearing range. And so if you don't block 60 hertz noise, somehow, somewhere, it hums, right? It's low frequency, but it's annoying. And it can get all of its harmonics, and then that gets really annoying, right? So notch filters are your friend. All right, basic terminology. Here, when we're looking at the corner low pass filter, right, we call these our corner frequencies, right? Because that's where it makes the corner, it turns the corner. If it's passing it, we're not rejecting, we have a pass band, okay? The corner frequency is also called the 3 dB point, or minus 3 dB point. Realistically, in conversation, I've never said minus 3 dB point. I always just say the 3 dB point. Most people tend to be that way because they don't like to say as many words. There is this also issue when you design like a real filter, especially more advanced filters and digital filters for sure, right? Where you'll get kind of bumps that go on forever. And so that region, once it's off, is called the stop band. Now the stop band isn't some defined thing like F1, which F corner, I'm going to F corner FC it so that I don't keep calling it F1, FC. The corner, it's not like the corner frequency, which everyone in the industry agrees is 3 dB. The stop band is a user-defined value that once the signal is below that point, that's the stop band. That's all it is. You generally, okay, this one's a little bit weird because depending where you are and like your company even or your class, some people don't like to call a band pass or a notch filter points 3 dB points or corner frequencies. I do, to be honest, but it's kind of confusing because you don't have a corner frequency, right? So you have yes. So they'll refer to it in terms of F naught, the center frequency. So you have the center frequency with the bandwidth, right? Makes sense, it still works. Most of the time when I talk about it, I'll say a pass band from this to that, from A to B, from 30 to 50 kilohertz, whatever it happens to be. I think we're all familiar with the term bandwidth, right? The bandwidth of my amplifier, the bandwidth of the filter. One of the things that you may, I'll come back to that actually. Generally speaking, your pass band is going to be symmetric around F naught. It does not have to be, right? Because we can build different kinds of filters, right? One way of building a pass band is I take a low pass and a high pass and I stick them together. And then I end up with a band pass, right? In that case, I could have like a second order low pass and a first order high pass, and then they would actually have different slopes. But generally speaking, we expect them to be symmetric around the center frequency. It's just kind of a reasonable expectation when we talk about it. There is an issue with both notch and bandpass filters, where if they're broad relative to, I'm going to just call I'm going to give them labels F1 and F2. If the distance between F2 and F1 is broad compared to F0, then it's fairly easy to design. If it's small compared to F0, it's harder to design. You run into some interesting complications. So there's a kind of a rule where the ratio, and you can also just look at it as the ratio to F2 to F1, right? Rather than looking at it as F0. So one of the ways that you define it is if you say F2 to F1, the ratio, because F2 is always going to be bigger than F1. If this is less than somewhere between 1.1 and 1.7, depending on what book you're looking at, this starts running into some issues around the design and making it with, well, I'll talk about that in a bit, but making these is more complicated. Like if you build one that is wide and go, okay, I'm just going to use that same architecture to build a narrow one, it might work, but there's this next idea of the Q factor or the quality factor, right? Which is, for all intents and purposes, really just a description of how good the filter is, more or less, like how good of a filter is it. The actual definition is more something like the ratio of the center frequency of a bandpass filter to the 3 dB bandwidth or something like that. And you can find the Q factor. I'm not actually going to do it, but right, if you represent the filter as something like AS squared to BS plus C or something like that, you use this formula to extract the Q factor. I'm not going to make you do that. That's not really interesting because a lot of times in circuit design, like calculators, you can kind of specify a minimum Q factor. Like I need it to be this good. Yeah. Great. There are some other kind of non-ideal issues that we need to deal with in filters, and this is a real issue. So I should just erase that one, but I'm going to redraw a low pass filter. And we would like it to look like so, would be kind of our ideal. But if we go and actually build this, depending on the type of filter we build, it may or may not actually be shaped like that, right? So one of the things that can happen is there's a thing called a Chevy-Chev filter, right? That tends to have, I'm going to just draw it above really and pretend it's the same, but right, it tends to have a lot of ripple and it has a big bump before descending, right? That's kind of the characteristic of a Chevy-Chev. Your typical RC filter, right? Your passive filters are going to have this kind of smoother roll off. They're not going to go unstable. But then your active filters, so we'll talk about those terms a little bit more in detail in just a moment. But right, you have passive filters where you take a resistor and a capacitor or resistor, capacitor, and inductor, and you throw them into a circuit, and that's your filter. You can also have active filters. Active filters want gain, right? And the bandwidth of those is going to be limited by the op amp, right? So let's say I build an active filter and I want a low pass filter cutoff. What often ends up happening is this same kind of thing, which we call peaking. And it might do realistically, it should probably technically be mostly parallel. It does not actually have to be exactly parallel, right? Non-idealities happen everywhere. This peak actually once you start, how do I phrase this? So I was designing a circuit and I did like a million iterations of it because it was a very precision circuit and it was very frustrating. It got to a point where I could just look at the peak on this and tell you what my phase margin was. You don't know what phase margin is? Does anyone not know what phase margin is? Okay, I'm gonna queue up that. I will. Aren't you an EE? Justin? Yeah.
Yeah.
Micro 1.5.
Yeah.
Okay. Okay.
I was briefed in that class, but I couldn't give you a definition. But
Exactly.
I have a big idea.
I thought you were pointing at Jeremy, not me. That's why.
Nope.
Oh, thank you.
Sorry. Yeah. I don't mean to put you on the spot. I was just surprised because phase margin, which I will actually talk about a little bit more. I just made a note.
Well, we don't like EMAC samples.
You want wide phase margins, so you have stability. That's all I remember.
Don't worry. Phase margin as a concept is really easy. Negative feedback, whatever. I'm not gonna draw the rest. Okay. Say I have an inverting amplifier configuration. Right, this is negative feedback. It's going to subtract it. Well, if I put a capacitive load at this, right, capacitors have an effect on the phase of the signal. Well, if my signal input is that, and I subtract something with a little bit of a phase shift, everything is fine, right? Conversely, if I do this and I end up perfectly out of phase and I subtract this, well, this 1 minus 1 is 2, right? And suddenly I'm in positive feedback because the phase shift. That's all phase margin is really talking about, is how much room do I have in the phase of the signal before I end up actually in positive feedback. That's the conceptual level. There's a big math term around it that I'll not dig into, but I'll think about if I need to present you more, because measuring things like phase margin and LT spice is kind of a very common thing that we'll do because of the peaking issue. Because if you don't have enough phase margin, right, there's this kind of rule that you need about 45 degrees of phase margin to be okay. Realistically, you can kind of push that down to 30 degrees, but any more than that, and your circuit will go from working to not working to working to not working, and it is terrible to debug. So you'll see graphs that kind of do this. So if I pull up an amplifier, it'll be like, this is the plot with C sub L equals 50 pico. And this is the graph when CL equals 100 pico and so on, right? Because the more capacitance, the more phase shift I'm going to get, the less stable my amplifier becomes. This is all itself a problem because back to the issue where if I'm trying to de-embed the roll-off and I'm expecting 3 dB down and I'm really getting 6 dB up, and I'm going to get a very bad signal, right? So it's important when you're designing any precision type circuits to actually characterize your circuit. So I will probably actually have you guys do this with one of your filters, and hopefully I can get to a point where it's nearly unstable. And it's really kind of fun because the best way to do it, right, is we have these things called spectrum analyzers. Has anyone gotten a chance to use those in this program?
Yeah.
Sweet. Yeah, right. Where it puts in some sort of stimulus waveform, and it could be like white noise, or it could be a series of sinusoids, and it measures the input versus output. One of the features that it can do, right? Well, you can actually do the same thing, right? Is I can put in a sine wave of 1 volt per volt and assume that I have a gain of 5 or something, right? And I expect 5 volts per volt. Well, I just slowly turn up the frequency right on the function generator, and it should be 5 volts, 5 volts, 5 volts, 5 volts, and start rolling off. And then I should be able to calculate, well, at FC, is it 3 dB less than the passband? Or does it go up as I kind of increase that frequency on the generator? And this is kind of the cheap way of doing it. So when I started out my PhD, it was kind of a new research lab, and we didn't have the spectrum analyzer yet. It showed up eventually. And so I was characterizing a lot of my circuits by manually increasing the frequency and just putting in Excel the points, and I could plot it. And make sure that it was doing what I thought it would. This can be, right, you can kind of, you should know roughly what it is most of the time, but it turns out if you're doing kind of experimental work, sometimes you actually don't know what the capacitance, the capacitive load of your sensor or whatever it is you're working with is. It's kind of an unknown capacitive load. This has happened to me more than once. I don't know how common it is outside of PhDs and national labs and research settings, but I run it into enough times that I'm like, it is an issue of unknown capacitive loads that then I need to characterize to figure out what it is. Now, if I had had you guys have a 3120 prereq, which I didn't because I like the CEs as much as the EEs, we could go ahead and show this other interesting phenomenon where if I have a multi-stage filter, for example, which I'll talk about in a bit, and I end up with capacitance at the input of these amplifiers, turns out capacitance at the input of the amplifiers also makes them unstable. Too much capacitance at the input leads to stability problems. So anytime you're designing any sort of precision or wideband amplifiers, your biggest issue tends to be around stability, right? And that's what controls talked about, which I think everyone, I don't know, do Cs have to take controls? No? Okay, good to know. Yeah, so controls talks about stability of closed loop systems, which is ultimately what phase margin is all about, is how stable is the system. Okay. I may run out of voice before this class is over. Okay, passive filters, right? Passive filters being defined as things without op amps, things that are basically using resistors, capacitors, and inductors. These work really well from about 100 hertz up to 100 megahertz or beyond, right? They're not perfect. Now, the reason we say 100 hertz is a couple of reasons. The first one being that anything below 100 hertz, right? We built below 100 hertz, but we didn't really care. We weren't that precise. But you may have noticed that your capacitors start getting really big, right? That's a problem in and of itself if you're trying to build a system that has to go in some limited size box, right? So some of the, one of the master students that I graduated with, so he got his master's at the same time I got my PhD, he was designing components that actually went like inside of the drill rigging that was going down into oil drills. And obviously that had some low frequency vibration issues that they needed to filter out, because as we talked about with mechanical sensors, and you can imagine real quick, right, with your force sensor, if I walk by the force sensor, it jiggles and it disrupts my measurement. So I want just the slow signal, so I'm real low pass filter to get rid of kind of the lower frequencies. But suddenly I need to use it, you know, say I have 4 instruments, I need to use 100 microfarad capacitors, and they're suddenly, you know, that big around and that tall. It's a problem, right? And the higher voltage, the bigger they get, right? So on the low frequency, that's one of the issues. It's just the size of the parts get ridiculous. Also the cost starts to go up the bigger they get because they're bigger, right? So things like inductors get really expensive and really not very accurate when you start getting to low frequencies. The other issue is when you have a capacitor, right? We draw it like this because it is more or less this, right? It is just 2 parallel metal plates with something in between them, and they accumulate charge on one plate, and we end up with the kind of characteristic curves we all know and love. The issue is we tell you that these block DC. That does not really work that way, because whatever is here actually has some conductivity to it. It's not very much. Well, it turns out that if you were to go look at a plot of the characteristic impedance of a capacitor, it looks something like this on a log scale. And if I go up, well, let's say this is a 10 microfarad. and I do compare it to a 1 microfarad, where this is resistance also log. I get more resistance the smaller my capacitance is, which doesn't surprise, right? Because it's basically, you can imagine parasitic resistances that kind of go between this, and the wider it is, the more parallel elements that I have, right? The bigger it is, the bigger issue becomes. We call this leakage current because it leaks. It's not supposed to be there. It's a parasitic element, and the bigger it gets, the worse that gets. So we would like to have these really big capacitors that don't leak, but that's just not the case. So there is some kind of fundamental low limit to this depending on the precision that you need for your amplifier, right? And it's going to correspond to things like, what are the characteristics of your sensor? So there's this really kind of fun thing that I wish I got to talk more about, but eventually, when we're doing some precision circuits, especially in integrated circuits, which is kind of my background there, we don't use resistors in the feedback, we use capacitors. And you can use these capacitive feedback networks. And the huge benefit is in an integrated circuit. So say I'm not using op amp, say I've designed an IC amplifier, right? Anyone have a guess why I might use capacitors instead of resistors in my feedback? Yeah, it's easier to build, specifically because capacitors are much smaller than resistors. Resistors are very big as far as ICs go, or you have to use what we call active resistors, right? That's the other one that you do, and you use a transistor as your resistor. But as anybody knows, this is not very accurate because that resistor changes with things like pressure and temperature, right? And in fact, if it's jouling, that's enough force on really precise measurements to actually introduce noise into a transistor that's moving. So anyways, transistors have their own issues, capacitors have their issues, right? They all have these kind of trade-offs that you have to evaluate. How do we build them? I may find an excuse to have you guys build a capacitive feedback amplifier, but I don't have that one yet. And one of the ones I went and just pulled up a data sheet, actually, just so I had some numbers. So one of the capacitor families, they have a 1 microfarad that at 1 millihertz. Okay, so they went really far down to go ahead and measure the capacitance. Its resistance was only 1,000 kiloohms if it was 1 microfarad, but if it was 0.1 microfarad, it was 10 times. It was 10 kiloohms, right? So basically what it was coming to is every decade of capacitance corresponded to a decade's worth of increase in resistance. So at 1 microfarad, if you only have a kiloohm of DC resistance, that's a lot of leakage current potentially, right? And if you go 10 times that big, and 10 times it starts to be a problem. Now, you'll choose your capacitors based on their qualities, right? And I'm not going to go into that in this lecture. So I'm going to run out of time as is. But you're going to choose your capacitors based on various properties, right? Because there's not just one kind of capacitor, right? There's like, what do you guys know? Actually, what do you guys know in types of capacitors? Ceramic, electrolytic, pause caps. No, I've never used those ones actually. And then tantalum's the other major one that we look at a lot of times, tantalum capacitors. Yeah. Okay, so be aware that your capacitor choice actually matters in precision measurements. And that's always what I think about when sensors, right? Is like designing non-precise sensors is really easy. Designing good sensor systems is hard. To save some time, I was going to go through and cover various like how you build low pass filters out of components, but you guys can Google that really easy, right? You can build low pass, high pass, band pass. You just Google how to do it. And I'm going to save you that at the moment because I don't think I want to spend the time considering how little time I have left. Well, I mean, what, 6:15 that it ends at, right? I think I can do this. There's just one I want to kind of talk about. So the books have this kind of issue where they haven't necessarily like built real filters. They just kind of look at it from academic standpoint. And when they go ahead and say, let's build a bandpass filter, they do this. Right? That's my bandpass filter. And you can kind of tell why, right? So it's really an RC makes it a low pass filter, but then when the inductor kicks in, it kind of starts to negate those two, right? They kind of interact. So there's some intuitive level of why that's a bandpass. And it's kind of obvious. It has to be one or the other, right? Bandpass or a notch, right? One of those two, it has to exist. The notch filters are actually really similar. Right? And these just create some resonant frequency, which turns out to be your F naught, right? So bandpass, notch. Now, does anyone see what the issue with this, like actually building this in a circuit is? The inductor, they're really not very good. And they're very expensive compared to other components. So if you're trying to turn this into like a mass production kind of thing, not very good. So what we often end up doing realistically is we spend more components in order to not use inductors. Because it turns out I can use more resistors and more capacitors and still be cheaper than my inductor. So basically drawn as a block. Right, stick them together. It doesn't matter what order I put them in. Now, as long as they're linear systems, right? Which if they're passive components, they're linear. Right, that's what linear means. Okay, just checking. And so you just stick two of them together, and now you have yourself a nice bandpass filter. Now, this doesn't work very well for narrow bandpass, right? When I start reaching that ratio of F2 to F1, this starts having its issues because, well, this is what I want it to look like, right? And in an ideal situation, this gain is just 1, right? That's like the best that we can do, right? Passive components aren't going to make the signal any bigger. Well, one of the issues is because they start playing into each other, they start having issues. The other one is kind of this pole proximity issue, is that the closer you start putting two poles, the less stable your system is going to be. And there's this whole discussion about it that I might squeeze in at the end about you can design these really cool circuits that rely on taking two poles and sticking them together. Like if you land two poles exactly in the same spot, oh, sorry, a pole and a 0 in the same spot, they cancel out and go away, right? Well, it's true, and it works well in math, but if you're trying to build passive components with 1% or even 0.1% accuracy, they're going to move. And so like one of the papers that I was working on publishing that I never quite got to was a discussion of that pole 0 cancellation and what happens relative to if the pole leads or lags, right? And it actually changes the characteristics when you're trying to cancel out these really narrow ones. So it can have, depending on how you're implementing this filter, it can actually have some stability implications as well. Okay. So I'm going to transition to active filters, right? Active filter just means I'm going to bring some amplifier into it. One of the big benefits of amplifiers is I no longer need inductors. Inductors are really inaccurate measurements. The other one is, right, my filter can now have gain, right? It doesn't have to just pass 1. Now, the benefit, a lot of times you will have a gain of 1 in your filter and then you'll gain it up somewhere else. And the main reason that you would do that is along the lines of, well, one of the main limiting factors of your active filters is the simple fact that you are limited by the bandwidth of your amplifier, right? So if you go and read Practical Electronics for Inventors, it's going to say something like, actually, I think I wrote it down because it made me laugh a little. An active filter is limited to less than 100 kilohertz-ish. No, I don't actually know when this book was published, but it turns out that 100 kilohertz is a little bit unfriendly. It makes sense to put it in like a hobbyist book, but it's kind of propagated because this book is so popular. If you like Google it, it's like, oh yeah, don't need over 100 kilohertz. Well, yeah, sure. Don't go over 100 kilohertz on like a breadboard, right? It just gets hard. Building it at 1 megahertz is pretty trivial. Like if you're careful, I mean, you can probably do that on breadboard if you're really careful and neat. You can almost certainly do it on like a proto board, right, where you solder stuff down. 10 megahertz starts getting tricky. In fact, 10 megahertz is kind of fun because it's still like within this realm of reasonable that you don't have to worry about transmission line effects yet. It's not, the stability is not an issue. It's pretty easy to find an amplifier with a sufficient gain bandwidth product, but it's requires some interesting thoughts, right? And so this is, for the moment, kind of an academic point, but it's kind of fun to consider what you can do when you start leaving behind the undergraduate mentality, right? That's kind of what this course is talking about, right? Sensors aren't ideal, op-amps aren't ideal. A lot of this is about the non-idealities. Well, one of the things that you tend to learn in do this weird, but I'll stick to it. In your undergrad degree, and I'm going to pretend all of you undergrads are masters because this is kind of a master's level class regardless, and I'm sorry that your electives work that way, but that's how it goes. You've been told that positive feedback is bad, right? We don't like positive feedback. Well, it turns out that it's actually very useful. So this is actually from Texas Instruments app note where, oh, sorry, this placement is not quite right. This is positive feedback, right? Here we can see that we have a low pass filter. So this is either going to be a low pass, band pass, or notch filter. We know that already, right? Well, let's kind of look what happens, right? So at low frequencies, this is blocked, right? This is open, and it looks basically just like an inverting amplifier that provides gain. So at low frequencies, I'm a low pass filter. Makes sense, okay? Well, as I go to high frequencies, this thing kind of shunts out and we actually bypass this whole amplification circuit. So if I have any gain here, right, I've now gotten rid of it and my signal just goes to the output with this kind of divider, right? So that positive feedback is kind of eliminating gain at higher frequencies. So it's actually functioning as a low pass filter, right? Well, it's really cool and it actually helped. The issue is that nothing is ideal, right? So it does what we would like it to, is it comes down, but it ultimately hits some point where you start getting kind of parasitic poles and zeros, and mostly in this case zeros, that kind of start adding up. and it starts doing that, which is a bit of a problem. Now, this guy keeps rolling off, and eventually the parasitics add up, and it kind of, who knows, it looks really, truly awful when you do that. But I just like to show this because it turns out the positive feedback is really useful, because this allows us, this architecture allows us to push FC to 10 megahertz. Pretty easy, actually. As long as your stop band doesn't need to be too much below your pass band. Overall, this kind of architecture is really common when you have an active amplifier where you have a low pass filter at the input and then kind of buffer that for gain and additional filtering. I think I can actually just modify this to illustrate the point real quick. I'm just going to draw it again. So like, let's say I'm going to switch and I want to do something like a 3-pole passive filter, right? If I didn't want any gain on it, I could really just do RC, 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 right? They have some interaction between each other. You know, it's not like ideal, but you can do it. So let's go with like the simplest 3-pole. Or we'll start out with a simple 3-pole, right? Low pass filter number 1. Low pass filter number 2. These two kind of depend on each other, right? They interact. It's not as simple as this pole and then that pole and so on, right? There's a bit of an interaction with these resistances because if I put an op amp here, I have infinite impedance, right? And this pole is exactly where I put it. But if this is not infinite impedance, it kind of has a bit of an issue. To prevent further cascading errors, I could throw an op amplifier in here right now and have infinite input impedance. But let's go back and look here using that kind of lesson from the last one we had, where if we split this resistor in two, right, this resistor splitting thing is kind of really common in circuit design. We start getting to precision amplifiers and unity gain. C1. Now we're in negative feedback with this capacitor, right? And I actually just added myself another pole here. Now, if I was really cruel, I could go make you do the math. I think actually Practical Electronics for Inventors sets the math up for you and kind of walks you through. They have this kind of weird way of doing it, which is I don't like. So if you go read this book, they do this thing kind of called like a normalized filter, where they're like, all right, let's design this filter to have a bandwidth of X. And we're going to do it using strictly 1 ohm resistors. And they go through and their default capacitor, I think they, yeah. So what they do is they say, let's design it for our algebra using 1 ohm resistors and mystery level capacitors. And then they give you a table like you're a mechanical engineer, because mechanical engineers like tables, and this book is really for mechanical engineers. And they go look up on a table what C3, C1, and C2 should be based on this 1 ohm architecture. And then they just scale it up, right? Because this, if I have 1 ohm resistor, right? So it seemed wrong, right? And I'm looking for some corner frequency and R is 1, then C is going to be something like 100 micro or something ridiculous. And so then they just start tinkering with those values based on some table to get a non-normalized thing. It's a weird trade-off between like doing all the math yourself and just plugging it into a calculator. So I'm going to lean more on the calculator side. I'm not going to teach this normalized math thing because you're not going to be sitting at work with no computer. And if the internet's gone out, you have bigger concerns, I think. Anyways, yeah. That is an example of a 3-pole low pass filter that you would go find a calculator for and enter it in. And does anyone know what the issue with 3-pole passive or active filter is compared to like a 1-pole? Right. Just for clarity. Phase margin. Yeah. Right. In case you guys don't know, because I'm not going to take anything for granted if that's not clear. Right. If a 1-pole looks like this and I'm descending, you know, per decade, if I add a second pole at the same point, it descends faster. Right. Unfortunately, each pole you add takes away phase margin. Makes it harder and harder to keep it stable. This book has one really cool thing is it actually has really good examples of various filters. Like when you finally get to like the more advanced multi-stage high pass, multi-stage low pass, because it's kind of nice. It turns out that for the most part, if I design 2 active low pass filters and I just chain them together, their stability is mostly independent. It's just when I'm trying to do it all in one stage. Now the trade-off here is obvious, right? One stage saves me money because the most expensive component of this is the op amp. Clearly, whatever I do, it's going to be the op amp. So this one is 3 poles, 1 op amp. Yay, saves money. This one is 2 op amps. It just costs me more money, but it's more stable. All of that added stability goes away if you have to close these filters in feedback, which we do fairly often, right? Because now these poles are within the feedback. If the feedback is closed, they interact with each other and they lose phase margin, which is still a mysterious word to you guys. The notch filters are really fun. I want to find an excuse to make you guys build a notch filter because they're entertaining to build. In case it's not obvious, LPF is low pass, HPF is high pass, right? And shoot, I screwed this one up. This isn't right. Yeah. There we go. Yep, that's the right one. If the book is wrong, I don't know if it is or not. I pulled from a couple of resources. The practical electronics, which I don't think I had you guys buy right. I had you guys buy the other one. I haven't checked this one if it even has the notch, the one you guys have. If you want to do electronics like hobbyist stuff, this is actually kind of a fun book. If you want, your career to be your hobby, like psychopath. Anyways, it's going to use like 1 ohm resistors in here because it's weird. You're going to go find a calculator. The issue with that one, yeah. This one is really easy to build and it's really fun. The issue is its Q factor is really bad, right? Circuits are all about trade-offs, right? And that's one of the ones I want to familiarize you guys with, which are kind of the trade-offs of things. If I want a better Q factor than that, I can actually build one, right? Unsurprisingly, it just costs more money, and it costs more money in the form of an additional op amp. this is probably going to be a potentiostat or something for fine tuning. Yeah, right. I add more components, add more stuff. Anytime you see something like this, right, this is really just a summing node. Right, because if I want to add two numbers together in analog electronics, this adds them together, right? And so this is just adding things together, but with some filtering, right? It adds, the addition depends on frequency, that's all. Right, there is some frequency where they're adding it the same, and then sometimes it's weighted. So that's my time, which is actually perfect. I am out of book too. So anyways, this is your introduction to filters and what filters are doing, why we use them, some of the considerations. With the audio amplifiers, we'll pick up, there's some interesting filters that are required for audio, especially for the active noise cancellation. So one of the filters that I will have you actually design for the active noise cancellation is what's called an all pass filter. Passes all frequencies. Why might I want to introduce an all pass filter into a system? That's one reason, actually, that's a good reason. Change the phase, right? Because any filter is going to change the phase of it. And if you have an all pass filter, you can actually, especially if it's an active filter, you can use your capacitors to choose the phase shift. And so when we get to the audio cancellation stuff, right? Everyone knows, that sound is, right, a wave, it's a summation of waves. Something, right, that's the audio with principal and secondary components. Well, once again, if I add this to that, it's 0, right? So if I can do something really cool, like have some headphones on and a microphone on the outside, and it measures the noise that is on the outside of this headphones and not on the inside, then it adds the noise that it measures on the signal that it measures on the outside to the noise, the signal on the inside with a phase shift, and it goes away. Right. And if you have some really nice headphones, then like I have some active noise cancellations that if my wife is talking to me and they're on, I cannot hear whatsoever. So they're pretty awesome. I'm not 100% sure the circuit will work when we do it because I have to figure out how to get you guys headphones that are like over ear that are affordable. I think I can do it, but I'm gonna find out because in-ear ones are kind of boring, right? And anyways, that's what we're gonna try and do. We're gonna try and create active noise cancellation. You're dismissed. Let me double check.
Oh.
Say I can't drill from the back door. not take out any other signal lines. So how do I connect something only to the bottom of the hole, not inside the jet?
Yep, that's the fun one. Is it's like Max. You use a technique of wax melting, where you take a small metal pin and you stick it through the center, and then you melt the wax around, and then you extract the metal pin.
And then you fill it with solder or something.
Yep.
Okay.
It turns out that as long as you have sufficiently fine solder, your pin can be soldered. Then you don't have to worry about trying to get the solder down that little hole.
Okay.
I don't recommend trying it.
What do we have to lose?
Time.
Oh, time. Okay, that's fair.
No, if it wasn't for
Have
time.
to lose. I'm just kidding. He's like done with all his stuff.
Well, you got to build up your ADC part still. Once you're done with that, you can tinker with extra boards all you want. But
Yeah, do that first. Then we'll.
That's like, they're like 10 more components.
Yeah.
Because
Also,
both of
we
the
realized
both of the
we
ADCs
can't
are-
use the SRAM like as data pins because there's different voltage levels. Because we had 1.8 and our dev boards are 3.3. So
question.
we're just gonna use the dev board like without that.
Okay, but does that 1.8 volt power bank power anything else besides the SRAM? What?
FPGA and Cypress, well, not Cypress isn't important. The FPGA is auxiliary. So So it does interposing between higher IO voltages and.
Okay, does the aux core have a voltage
Has to
range?
be 1.8.
Okay, so there's your issue. Because otherwise, most of the IO power banks don't care.
Yeah.
But it needs 1 volt, 1.8 volts, and some IO.
Okay.
And we tied
Yeah.
right together.
Let's see, I was hoping that you were not tied to a core. Because then you could just change the bank voltage and you're done.
We could probably change the. Can we change the bank voltage without the cord?
They're one plane.
That's fine. It's too bad, but you know.
But at this point, I mean, it's gonna work okay.
At this point, it's 80% of the effort I put in. It's now. Don't want that to happen.
You got to taste of grad school or like PhDs.
Yeah, but
I would rather
PhDs
drill through that.
are like done when you're done, not when the semester's over. No.
Yeah, it's kind of one of those things. I like look back at my PhD and I could recreate everything except for the animal experiments in like 2 months, beginning to end. I could do everything. Well, animal experiments and actually writing the papers, because that takes way too long. And then I would only need like 4 more months to do all the animal experiments. So I could do my whole 5 years worth of PhD in less than a year. Because most of your work is wasted. And don't worry, that won't change when you go to industry.
But you're paid for that.
You're paid in a PhD. A little.
Sure.
Eventually.
No, you get paid.
No.
Doing it, paying to do a PhD in engineering is psychotic. It's so easy to get paid to do a PhD, but you still get paid very much.
Yeah.
And so I sold that. And I got my 50.
I was wondering about this headphone noise cancellation.
Yeah.
Is that
I might
phase shift
just-
calculated based on the
0.5
distance?
versus-
each
It is. That's why I need the overhead.
Now it's like updated.
What if we were to do it?
Remember,
like
you're gonna do
open
liquid.
source, so it's-
They do actually. One of my really good friends, he did his whole PhD on exactly that. Because it's an industrial problem where the machine operators have a trade-off between safety of being able to hear and protecting their ears so that they're not deaf. So due to OSHA regulations, they have to wear headphones.
Yeah.
But, and even with a lot of the, like, the standard over-ear active noise cancellation just isn't enough to do anything. So what they end up doing is like loudspeaker active noise cancellation. So the issue with that is there's a
You got
sphere
reflections.
about this big that is fine. That is like really well canceled. But you go outside of that, it starts getting louder and louder because you have the additive noise cancellation.
And so that way I can
So they do it. It's actually really fascinating, but it has problems.
That is pretty cool.
And then if I want to run my algebraic stuff, that's
Be fancy to make the machines emit their own noise cancellation on them. So the source of the noise is canceled.
Actually,
That's kind of impossible because it's not just
even run
because-
CAS in RPN.
Like I'm thinking like a milling
'Cause the
machine, noise is
machine-
gonna come off of the milled metal. You can't
it does, but it
cancel
comes off of not just the milled metal, it comes off the entirety of the milled metal and the entirety of the machine. So it has all of these sources. You can't replicate that with the point
Do you
source.
guys have the, I don't know if it comes with the, I updated a while ago, we have Python.
Yeah.
That'd be fascinating. Though. You just have a dead zone of sound around you.
Oh, that is pretty interesting.
So they do try it, the active noise. There's like active research around trying to silence tanks, right? Military wants to be able to drive tanks and make them quiet so that they're really loud if you're behind them because you need the sound to go somewhere, right? Basically, but it's super quiet, so you have less warning if they're coming up to you.
What if I decide to have a little seismometer
I
that
got
I just kind of carry around? It's like, there's a tank coming.
Well, that's a win, right? Because now the opponent needs seismometers with every squad, or they get ran over by a surprise tank.
While I'm doing homework.
So, yeah, no, that's a win. If you make someone else have to buy equipment,
The tank driving and you're emitting.
yeah, sound cancellation.
Destructive.
Destructive interference.
Destructive constructive interference.
It's just destructive interference.
Useful destructive.
Yeah, there we
That's
go.
what
That's
you're
what I'm
looking
looking for. Useful destructive interference.
Yeah.
Bring it back.
What are they grabbing?
They're putting something away.
Oh, gotcha.
I hate it, I hate entering.
Something like these, is what you're looking for?
Yeah, do they have a 3mm? Yep.
Yeah,
Yep.
they have one on both sides. You can actually use the channel.
Oh, that's
actually kind of cool.
Yeah, exactly like that.
Okay.
I have to make sure it works. Actually, that's not true. We can fail together.
Okay.
Failing is educational.
I agree.
So you can look at this.
For the most part.
Okay, that makes sense.
If it wasn't, I would have learned anything in my PhD.
The biggest downside.
I didn't learn anything from my successes. Not really, because by the time I succeeded, I understood it and I was done learning.
But. And Mitch and
I wish they were better about communicating that to freshmen.
Because of the nature of our time.
Yeah, you fail, you get set back.
Yeah, well, and you feel bad, right? It's demotivating for freshmen to fail. I don't mean like failing in class, because failing in class sucks, but like failing at endeavors, like struggling through is fine. Being frustrated at something is a sign you're learning something.
Yeah.
And I tell that to my 2700 students. I'm like, you're not frustrated, you're not learning. You're frustrated, you're doing okay, you're fine. It's that despair that can leave, that comes out of that frustration that is dangerous.
Did have that 50 has the equation writer. So like.
I don't know.
I mean, you can write.
Best
equations.
engineers
This is
are the
what-
ones that enjoy being
So, like,
frustrated.
Instead of like writing recipes, like, let's say how.
And it's not even necessarily enjoy, right? It's that enjoyment of getting over the frustration,
Yeah,
the
over the
success that comes. I actually just enjoy being frustrated, like oh, how do I solve this? Is an enjoyable experience. Because it's not life threatening.
Yeah.
You know, it's just perspective. And I was always, same as you, you know, I was always a good enough student that I was never under the threat of like failing in class. So.
Yeah, I have, the closest I've got was probably signals and systems. That's probably the closest I've
And then
got.
you hit enter. and then, well,
Mine was organic chemistry.
that way it'll-
That's the closest I got.
Brackets. for-
See, I haven't even gone that far.
You don't need to.
Yeah,
You just
exactly.
don't take OChem.
Yeah. Well, dude, that's.
That's what I like about it.
I think there's only one that says.
I have a lot of credit hours. I've changed majors a lot.
Oh, really? I think I have like 130.
Yeah, I have like 260.
Oh, wow.
I don't think I've.
That's supposed like 2 full degrees.
You know what
It's
I
like
mean?
a degree and 4 minors and 2 associates.
Yeah. Especially when I was doing like.
So I have an associate's in IT.
On my
bachelor's in electrical. I have minors. Actually, don't technically have one of the minors. I didn't fill them all out because there's just no point. It didn't do anything.
Yeah.
And I wasn't trying to get the minor. I just got them from changing majors too often. So it's chemistry, philosophy, math. I swear there was a fourth.
I didn't know that. That's cool.
Oh, that's what it was. Because I actually came to Weber for a little while, and before I transferred to the U, if I had just finished, my minors would have been philosophy, microbiology, and zoology,
Oh, wow.
which was just stupid.
That's funny.
And then the math came from the U because the only difference between for an EE for getting a math minor and not is one class.
See, and for us, we actually have the associates of math included if you split up linear algebra differential equations.
Yeah.
So I have that.
Yeah, I did it because all of my friends were, not because it held any real value, but it's kind of fun to be like, oh yeah, I have associate's degree in math.
Yeah. I did have one question for you.
Yeah.
If you had a perfectly balanced bridge, perfectly balanced half bridge, that would take out all the temperature.
Yes.
Okay, all right. I just wanted to make sure.
Yeah, assuming that both of your sensors were also perfectly matched.
Okay, that also makes sense. Okay. Gotcha. Well, yeah, but perfectly balanced bridge, your sensors would have to be matched.
Well, you can be balanced at 0 and not balanced at.
I guess that's fair. Think of it different.
Yeah, so at 35 degrees C, you're balanced. At 37 degrees, you're not because the thermal coefficient is different, that kind of thing.
Gotcha.
So I guess the perfectly balanced kind of maybe implies, but I don't know.
And how would you get around it?
You don't.
Okay.
You just do the best you can.
Okay. All right.
One of the things, well, the other one you can.
Or the controller,
Exactly. Yep. You measure, you pick a signal that you're measuring that you know it's supposed to be something different, and then you feed it back around, right? So you, like, for example, you could build a thermal system that actually measures the temperature specifically, right? So you can get very precise temperature deltas. So you start at a known temperature, you have the thermal temperature, and then you just measure the delta. Because measuring a change of something is much easier than measuring the absolute of something.
yeah.
And so you build a temperature sensor that has very high quality thermal characteristics, right? And then you do something like, well, if this is the output of my bridge, and these are my two sensors, and this is my signal output, and I measure the temperature through some op amp. And I just add some signal to this signal and fix it.
Interesting. Have you found like a useful book that's not awful?
No.
No, you haven't?
No,
Okay, so, okay.
I kind of gave up.
Okay. I was just looking for something that I could read a little more to get a better understanding.
Yeah, so you can read more. There are plenty of books. I can give you a pile of book recommendations.
I want a useful
But,
book.
Yeah, so the issue is, most of it is going to be useful. You're going to learn a lot. And in fact, I've learned a lot from reading it. The challenge is some of it's wrong. So I have to test, like the bridge issue. I thought I knew it. Yeah, because I learned it from this book. And it's even easier, so I was wrong, it turns out.
Okay.
So,
Emphasize this stuff. It's my favorite calculator.
I mean, it's this weird trade-off.
On the stack, on the prime.
So like, specifically, what would you like to know more about?
Click it, and then you click pick, and then it brings it
Just
down.
what we've learned,
Prime, just click.
how to reduce sensitivity or increase sensitivity and reduce noise.
Right. Yeah, I don't know yet. I haven't had a lot of time to fiddle through other books. I've just been swamped this semester, so doing the best that I can with the garbage that we got.
Okay, perfect. Okay.
And this book is actually one of the best, surprisingly.
The hobby one?
The hobby one is one of the more accurate because it's designed for people to use. So people actually test this,
Yeah, that makes sense.
which uncovers the issues. So if it's covered, this is actually pretty good. It does oversimplify things and kind of ignores parasitics and isn't really good for like precision measurements. But for the introductory stuff, is fine. And then you can use your overall arching knowledge of circuits to figure out what the non-idealities mean.
Okay. Okay, good to know. Thank you.
Yeah.
Yeah, but the thing is. Part of it.
That's true.
And just have everything you expect. Once you have clear. You clear stack.
Yeah, so like I was showing you this last time. This isn't all of them that I have, but so I've got a blue. I have a blue HP50, they call it Smurf, and then I've got a 50. I've got a 48 SX and I have a 48 GX in between there. Dude, so that calculator